All right, listen up. Welcome to this explainer on a topic that is absolutely crucial for your Cambridge computer science success, data defense, or, as you'll often see it on the syllabus, checking inputs. Look, we need to treat bad input data like it's a high-stakes vulnerability. It's literally an attack on a system's integrity that programmers, and you, as future programmers, must constantly defend against. Today, we're going to decode exactly how these automated defense mechanisms work, play the examiner's game, and build a rock-solid blueprint for answering any question they throw at you on this topic. Let's start the clock and jump right in. To truly master data defense, we have to start by looking at the reality of the threat. Ask yourself this: what is the single largest source of software inaccuracies out there? The real-world stakes here are incredibly high. Organizations rely entirely on the accuracy of their data to make decisions. Imagine a doctor receiving the wrong medical data about a patient, or a firefighter out in the field being given completely inaccurate data about wind speed and direction. These aren't just abstract ideas, they're life and death scenarios. So where do you think these massive inaccuracies come from? You might guess it's a hardware malfunction or some random network error, but the truth is actually much more human. The answer is the data entry process itself, the human element. That is exactly where the vast majority of errors happen. Because humans make mistakes, they rush, they typo, they forget things. Because of this, the ultimate line of defense for any software system is input checking. Systems absolutely must be designed to force accuracy during data entry. The data entry process is inherently flawed, so our code has to serve as the armor against those human flaws. Here is our tactical roadmap for this session. We've just established the threat of bad data. Next, we'll dive into validation, the 6 specific checks examiners love to ask about, and we'll crack the math behind the check digit. Then we'll explore verification, and finally look at how to actually code these defenses to guarantee top marks. Before we continue into Section 1, the threat and the first shield, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCS to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, let's look at the automated bouncers of our system. Now, if you were asked to define validation, this is the exact wording you need. Validation is the process of programming a system to automatically check that data falls within a set of specified input criteria. Pay close attention to the word automatically. It's the code doing the heavy lifting here. But listen, here is a crucial nuance that traps so many students. Validation cannot guarantee that the data entered is accurate. It only ensures that it is reasonable. It just filters out the obvious, completely illogical mistakes. For example, if a system is recording the heights of students, it's perfectly reasonable to set a rule expecting them to all be under 3 meters tall, right? By programming the system to reject entries above 3 meters, you drop the obvious typos. But what if a student's height was actually 1.4 meters and someone accidentally typed 1.04 meters? The system would accept it. Why? Because 1.04 is still under 3 meters. It meets the criteria, it's valid, it's reasonable, but it is entirely inaccurate. And that brings us to a massive conceptual trap that examiners test constantly: the difference between validation and verification. You must keep these two strictly separate in your mind. On the left, validation asks, is it reasonable? Does it follow our programmed rules? On the right, verification asks, is it accurate? Does it actually match the original source? Validation is the code checking the criteria. Verification is checking the reality. Remember, valid data can absolutely still be factually wrong. Moving on to Section 2, let's break down the 6 validation checks. These are your specific tools. Memorize this matrix. It's your ultimate arsenal for any scenario question. First up, the presence check. This simply verifies that required data has actually been typed in. The system will flat out reject groups of data where required fields are left blank, like trying to submit an online order without an email address. Second, the range check. This ensures data falls within a logical upper and lower boundary. For example, a percentage score in an exam literally has to be between 0 and 100 inclusive. Third, the length check. This ensures the data entered has a reasonable number of characters, like a password needing to be strictly more than 6 characters long. Fourth is the type check. This ensures the data item is a particular data type. If a stock quantity in a shop must be an integer, it's going to reject any input that has letters in it. And fifth, the format check. This checks that a data item matches a strict predetermined pattern, like a date of birth having to follow a day, month, year format with slashes. Let's look at how this logic actually functions on the back end. Here is a flowchart for a simple presence check. Notice the loop here. That's the key. Our algorithm starts by inputting the user's first name. The validation process then takes place entirely inside a loop. The core idea is that while the data input is incorrect, the algorithm refuses to move on and keeps giving the user another chance. It checks, is the data item equal to null or is it empty? If that's true, it outputs an error message and loops right back to ask again. If it evaluates to false, meaning the data is finally present, it breaks the loop and the program is allowed to continue. If you're writing a text-based console application, this is perfectly handled by a while loop or a do-while loop. Let's tackle Section 3, cracking the check digit. This is the sixth validation type, and it's heavily mathematical. A check digit is a brilliant piece of logic used to check that a numerical data item has been entered accurately. Essentially, an extra digit is added to the end of a number based on a specific calculation that the computer can repeat. This flowchart here represents the ISBN 13 check digit validation, which is the exact system used for book barcodes globally. When a barcode is scanned, the system performs this mathematical gauntlet instantly. I know it looks terrifying on screen with all these counters and substrings, but if you take a second to scan the core trend, it's just a loop. It's iterating through 12 digits, applying a math rule, and comparing the final result to that 13th digit. Let's break the math down step by step so you can replicate it. If an exam asks you to describe how a check digit is calculated, these are your golden steps. Let's use an actual book, ISBN 978-1108-935678. First step, we separate that final 13th digit, which is the 8. That 8 is our target. Second, we take the remaining 12 digits and multiply them by 1 or 3, alternating for every single number. So 9 times 1, plus 7 times 3, plus 8 times 1, and so on. Third, we add all those products together. In our specific example, that sum comes out to 122. Fourth, we find the modulus, the remainder of that sum when we divide it by 10. So 122 divided by 10 is 12, with a remainder or modulus of 2. Finally, we subtract that modulus from 10. 10 minus 2 gives us 8. Does our calculated 8 match the original 13th digit? Yes, it absolutely does. The number is valid. This mathematical weight guarantees that if a human typos even a single digit, the math totally breaks and the system catches it instantly. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. All right, let's get into Section 4, verification, the reality check. Verification is a process that helps to confirm the integrity of data as it's input into the system or when it's transferred between parts of a system. Now, data integrity refers to the correctness of data during and after processing. It ensures that the data remains a true and accurate representation of the original source. Copying data shouldn't change the actual data values. So if someone tries to tell you that verification makes data magically accurate, they are completely mistaken. Think about it. If the original paper form has a massive mistake written on it and you verify it perfectly into the computer, congratulations, the computer now perfectly holds a mistake. Verification confirms integrity from the source. It does not invent accuracy. So how do we actually do it? There are 2 specific forms of verification you need to know. First is the visual check. This is a totally manual process completed by the person inputting the data. Once the data is typed in, you literally look at the computer screen, then look back down at the original paper document and visually verify that they match. The second is double entry. This is where the data item is entered twice, either by 2 different operators or consecutively by the same user. The system then automatically compares the 2 input values to ensure they are identical. You see this all the time, right? When you're creating a new password online, the system always forces you to enter that exact same password twice before accepting it. Here is exactly what double entry looks like in pseudocode. It's your classic repeat until loop. The system outputs "please enter your password" and inputs the variable password1. Then it asks you to re-enter and inputs the variable password2. Then we hit an if statement. If password1 does not equal password2, then output passwords do not match. Try again. The entire block repeats until password1 exactly equals password2. But again, a crucial thing to think about here. Does double entry guarantee it's accurate? No way. If your caps lock button was accidentally pressed for both password entries, they would perfectly match each other, passing the verification, but it wouldn't actually be the password you intended to write. Let's move to Section 5, coding the defenses. How do we actually write this stuff? Take a close look at this error. System.invalidCastException. Conversion from string quote to type integer is not valid. This is exactly what happens when your defenses fail. Running code without passing the correct values to variables causes a program to completely crash or spit out unexpected results. In this specific case, no value was input by the user, so the system took an empty string, but the code was expecting a number. It is literally impossible to convert an empty string into a numeric value, which causes an unhandled exception error. In a real-world published program, the system would crash unexpectedly. To avoid this embarrassment, we must validate the data before we ever attempt to process it. To prevent that fatal crash, professional programmers use library routines like try-parse. Try-parse is a library routine that basically attempts to convert the input value into a specific data type that you indicate. If it's successful, an integer value is returned and safely stored in the required variable, and a Boolean value of true is returned to the system to indicate success. But if it's unsuccessful, say the user typed letters instead of numbers, it does not crash the program. Instead, it simply rejects the value, doesn't store it, and safely returns a Boolean value of false. Look at this specific try-parse command built into a loop. Do while int32.tryparse console.readline number equals false. This one single line of code is brilliant. It reads the user's input from the console, tries to parse it as a 32-bit integer, and attempts to assign it to the variable called number. If it fails, the whole thing evaluates to false, which immediately triggers the while loop to keep running, prompting the user again with not an integer, re-enter value. The loop will literally only exit once a successful conversion has been made. It acts as an unbreakable shield against those type mismatch crashes we just talked about. Now, while we are checking data types, we often need to validate highly specific formats, especially when dealing with text. This requires checking the individual characters within a string. Remember, a string is really just an array of characters, and commands like char.is allow us to iterate through a string and identify exactly what type of character sits at every single position. This is incredibly important for enforcing complex validation criteria. Here are the specific command variations you absolutely need to be familiar with. Char.isDigit checks if the character is a number from 0 to 9. Char.isLetter checks for A to Z. Char.isUpper checks specifically for capital letters, while Char.isLower checks for lowercase. Finally, Char.isSymbol looks for special characters. By combining a loop that iterates through the entire length of a password with these char.is commands, you can enforce incredibly strict security rules, making sure a user's password contains at least one uppercase letter, one lowercase letter, and a symbol. As we wrap this up, I want to leave you with the absolute golden rule of this entire topic. Validation does not make data input accurate. This is a common misconception. If you remember literally nothing else today, remember this phrase. Validation is just a shield. It protects the system from rule breakers. Verification protects the integrity of the data transfer. But absolutely neither of them can magically fix a human who just doesn't know what they are typing. I'm going to leave you with this final high-stakes question to ponder. If you build a flawless software validation vault using every length check, every check digit, and perfect loops, how will you ensure the human entering the data isn't simply making a valid-looking typo? The answer actually lies completely outside the code. It lies in proper training and better interface design, and in the fundamental understanding that systems serve humans, and humans are imperfect. Master this balance, and you've truly mastered data defense. Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCS to excel in your Cambridge examinations. Subscribe right now to acetheexams_IGCS and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here.